This short video is for some quick intuition building about the convolution as a multiplication operator. Let's say you have two polynomials. Let's call this left term x and the right term h, and you want to multiply them together. You can do this regularly, and it's pretty simple just by distributing and adding together. The other way is to consider the coefficients of each polynomial as their own signals. Again, this is x, h, and you can see x of n equals 1, 2, 3, h of n equals 4, 5, and then use the definition of the convolution by this sum formula. What you would do for each index of the output of y, let's say from n equals 0, 1, 2, and 3, compute the sliding window sum for all k. And that's what's shown here. And you have the sum of the elements of x, x of 0, x1, x2, multiplied element wise to an element of h as a sliding window with h. H is under time reversal. Now, there is a pattern here that based on how this is formatted, that this is actually a dot product of the signal x with the impulse response h staggered in time. I found this definition clicks more for me to understand rather than this crazy sum formula. And you'll see from this example that you'll get exactly the same answer if you did the convolution to get the coefficients this way than if you do it in the previous way. This is actually a good hint going forward about what the convolution is doing and why it is useful for certain transforms in terms of multiplication. As a sort of final reminder, you'll see a lot of people online or even the book uses table format for calculating convolutions between two signals. The book describes it as reminiscent of something like synthetic division back in high school algebra. I'm not really a fan of this table method, but it is a tradition of how to compute convolutions. I actually prefer the dot product intuition in my mind for calculating it.